In 1778, a Swedish chemist named Carl Wilhelm Scheele crushed a dark, greasy rock that miners had been rubbing on their cart axles for generations. They called it black lead. They assumed it was just another form of graphite, same slippery feel, same dark streak on paper. But when Scheele dissolved it in hot nitric acid, he realized this mineral was not graphite at all. It was the sulfide of an entirely unknown element, an element that would not even get a proper name, molybdenum, until his colleague Peter Jacob Helm isolated it 3 years later. For 2.5 centuries, that greasy black mineral sat at the edges of industrial history. Miners used it, gunsmiths swore by it, military engineers built entire weapons programs around it, and eventually, automotive engineers discovered it could do something remarkable inside the machines we drive every day. This is the story of molybdenum disulfide, a $2 mineral compound that might be one of the most underrated engine treatments in automotive history. Not because anyone banned it, not because corporations conspired to hide it, but because nobody could patent a rock, and in our economy, if nobody owns it, nobody advertises it. That is how genuinely useful knowledge disappears, not with a villain, but with a shrug. Stay with me through this one. By the end, you will understand the chemistry, the history, and exactly how to use it yourself. Let's go. Part 1. Why your engine is wasting more fuel than you think. Before we get to the fix, we need to understand the problem. And the problem is thermodynamics, specifically how bad your engine is at turning fuel into forward motion. Here is a number that should genuinely bother you. According to the US Department of Energy, only 12 to 30% of the energy in your fuel tank actually moves your car down the road. The rest, 70% or more, is lost. Lost to heat through your radiator and exhaust. Lost to friction between thousands of moving metal parts. Lost to pumping air against a partially closed throttle. Lost to powering your alternator, your water pump, your air conditioning. Toyota, one of the most efficiency-obsessed manufacturers on Earth, made headlines when their dynamic force engine achieved 41% thermal efficiency in a hybrid configuration. That was considered a breakthrough. Nissan is currently developing an engine they hope will reach 50%, and that project is described as pushing the boundary of what is physically possible with internal combustion. The average gasoline engine sitting in your driveway right now operates at roughly 20 to 25% thermal efficiency under normal driving conditions. That means for every dollar you spend on fuel, somewhere between 70 and 80 cents is essentially converted into waste heat. Now there are different kinds of losses, and not all of them can be fixed. The second law of thermodynamics puts a hard ceiling on what any heat engine can do. That is, the Carnot limit, and no clever additive will change the laws of physics. But within that ceiling, there are losses that come from friction, from incomplete combustion, from carbon deposits that build up on your piston crowns and cylinder heads over thousands of miles. And those losses? Those are exactly what molybdenum disulfide was born to fight. Part 2. The slippery rock that changed military history. To appreciate what MOS2 can do inside your engine, you need to understand what it has already done across 250 years of human engineering. Because this compound has one of the most quietly impressive resumes of any material on Earth. Go back to the mines of 18th century Scandinavia. Miners working molybdenite deposits noticed that this dark, soft mineral left a slippery residue on anything it touched. They crushed it and packed it around the axles of their ore carts. It worked better than animal fat. It worked in freezing temperatures when tallow turned to cement. And unlike graphite, it did not need moisture to stay slippery. That last detail matters more than it sounds. Graphite is an excellent lubricant, but only in the presence of water vapor or other condensable gases. Take graphite into a dry environment, high altitude, extreme cold, or vacuum, and its friction coefficient climbs dramatically. MOS2 does not have this limitation. Its lubricity is intrinsic to its crystal structure, not dependent on atmospheric conditions. This is because of something remarkable at the molecular level. MOS2 has a hexagonal layered structure, sheets of molybdenum atoms sandwiched between layers of sulfur atoms. The bonds within each layer are strong covalent bonds. But the bonds between layers? Those are weak van der Waals forces. Under pressure, these layers slide over each other with almost no resistance. The coefficient of friction for MOS2 crystals shearing along their layers is approximately 0.025, among the lowest of any known material. Think of it like a deck of playing cards. Each card is rigid and strong, but the deck slides apart effortlessly because the cards are barely sticking to each other. That is MOS2 at the atomic scale. By the 19th century, gunsmiths, particularly in the German-speaking world, had discovered that applying fine molybdenite powder to rifle bolt mechanisms kept them cycling smoothly in sub-zero temperatures where petroleum lubricants froze solid. During the Vietnam War, American soldiers used a commercial MOS2 product called dry slide to lubricate their weapons in jungle humidity. It was so effective that troops sourced it privately rather than relying on standard military-issue lubricants. But the real turning point came during and after World War II. The availability of high-purity molybdenum disulfide, driven by wartime demand for molybdenum steel alloys, spurred extensive research into its lubrication properties during the late 1930s and 1940s. American automakers Ford and General Motors used MOS2 to lubricate engines in millions of military vehicles. World War II pilots in the US Air Force carried MOS2 treated engines as a safety measure. If an oil tank was hit and lubricant was completely lost, the solid MOS2 film bonded to the engine's metal surfaces could keep the engine running long enough for an emergency landing. That is not a marketing claim, it is the founding story of WWII Moly, the German lubricant company, which was literally born from surplus MOS2 products sold in US Army post-exchange shops after the war. In 1946, the National Advisory Committee for Aeronautics, NACA, the direct predecessor to NASA, initiated formal research into MOS2 for aerospace applications. Those investigations led to MOS2 being used in some of the most demanding engineering environments humans have ever created, including the extendable legs of the Apollo Lunar Module that touched down on the Moon in 1969. Let that sink in. The same mineral that Swedish miners rubbed on cart axles in the 1700s helped land humans on the Moon. Part 3. Castor oil, the WWII fighter pilot's secret. Now let's talk about the second ingredient in this story, castor oil. And yes, the same castor oil your grandmother might have threatened you with as a child has one of the most distinguished engineering careers of any plant-based substance. In the early days of aviation, we are talking 1910s and the First World War, aircraft engines were a completely different breed than what we know today. The dominant design for fighter planes was the rotary engine, a bizarre and brilliant configuration where the entire engine block spun around a stationary crankshaft, with the propeller bolted directly to the rotating engine. The spinning mass provided its own cooling, no radiator needed. But rotary engines had a critical vulnerability. The fuel-air mixture passed directly through the crankcase on its way to the cylinders. Any lubricant in the crankcase would be mixed with the fuel and burned. Petroleum-based oils of that era were crude, literally. They would break down, carbonize, and gum up the engine within hours. Castor oil saved the rotary engine. Unlike petroleum lubricants of the day, castor oil maintained its viscosity under extreme heat, did not dissolve in gasoline, and burned relatively cleanly. The brand Castrol, still one of the most recognized names in lubricants, literally takes its name from castor oil plus lubricant. Their legendary Castrol R racing oil, with its distinctive sweet smell that vintage motorsport fans still rhapsodize about, is built around castor oil's unique chemistry. What makes castor oil special at the molecular level is its unusually high concentration of ricinoleic acid, roughly 90% of its fatty acid content. Ricinoleic acid has a hydroxyl group that makes it highly polar. In engine terms, these polar molecules act like microscopic magnets. They grab onto hot metal surfaces and form a tenacious boundary film that resists being squeezed away under extreme pressure. This is called boundary lubrication, and castor oil does it better than almost any other natural substance. The downside? Raw castor oil oxidizes quickly. It forms gums and varnish, which is why it was eventually replaced by synthetic oils in most applications. But chemists discovered that if you acetylate castor oil, a chemical process that stabilizes the molecule against oxidation, you get something remarkable: a clean-burning, thermally stable carrier fluid that still retains castor oil's extraordinary ability to bond to metal surfaces. This is where two historical streams converge: a polar, clean-burning carrier oil that clings to metal, and a layered mineral crystal that provides near-zero friction once it is in contact with a surface. Put them together, and you have a combination that tribologists, the scientists who study friction and wear, have been publishing papers about for decades. Part 4. The science. What actually happens inside your engine. So what does MOS2 actually do when it enters your engine? Let's walk through the real, verified science. No made-up journals, no invented studies, just peer-reviewed research. When MOS2 nanoparticles are introduced into an engine's lubrication system, they circulate with the oil and are carried to every metal-on-metal contact point. Piston rings against cylinder walls, crankshaft journals against bearings, camshaft lobes against lifters. Under the heat and pressure of these contact zones, the MOS2 particles do something that liquid lubricants cannot. They physically bond to the metal surface and embed themselves into the microscopic pores and valleys of the metal's surface texture. Once bonded, they form a solid lubricating film, a protective layer that persists even when the liquid oil film is momentarily disrupted, like during startup before oil pressure builds, or under extreme loads when the oil film gets squeezed thin enough to allow metal-to-metal contact. Engineers call this boundary layer protection, and it is precisely the scenario where engines suffer the most wear. A 2022 study published in Scientific Reports, that is, a peer-reviewed Nature journal, tested MOS2 nanoparticles dispersed in SAE 20W50 diesel engine oil. At a concentration of just 0.01 weight%, the coefficient of friction decreased by 19.24%, and the average wear scar diameter decreased by 19.52% compared to the base oil alone. The oxidation induction time, a measure of how long the oil resists degradation, improved by over 61%. Thermal conductivity of the oil also improved by approximately 10%. Another study, published in 2023 in Scientific Reports, tested hybrid MOS2 and carbon nanotube nanoparticles in engine oil. At 0.5 weight% concentration, friction at engine operating temperature was reduced by up to 26%. The researchers also investigated exhaust gas quality and found measurable reductions in particulate emissions. And here is where the castor oil connection gets particularly interesting. A 2025 study published in Clean Technologies and Environmental Policy tested MOS2 nanoparticles added to castor biodiesel. They found that the MOS2 widened the fuel injector's spray cone angle by 3 to 4.9%, and increased the spray projected area by 3.5 to 5.5%. What does that mean in practical terms? Better fuel atomization, better mixing with oxygen, more complete combustion. The fuel burns faster, cleaner, and more efficiently. Now, let me be honest with you, because honesty is what separates useful knowledge from clickbait. These improvements are real, but they are not magic. We are talking about friction reductions of 19 to 26% in the lubrication system. We are talking about measurably better fuel atomization and reduced particulate emissions. Over thousands of miles, these gains compound into real fuel savings, reduced engine wear, and a longer-lived powertrain. Independent fleet operators who use MOS2 additives consistently report fuel economy improvements in the range of 3 to 8%. Not 90%, but a genuine, measurable benefit that pays for itself many times over, given the low cost of the treatment. Part 5. Why you have never heard of this. So if MOS2 has been known since the 1700s, proven in peer-reviewed research, used by NASA, trusted by the military, and adopted by fleet operators, why is it not standard practice at every oil change shop and dealership in the country? The answer is not a conspiracy, it is economics, and understanding the economics actually makes the story more interesting, not less. Molybdenum disulfide is a naturally occurring mineral. You cannot patent a rock. Any chemical supplier can sell it. Any driver can buy a bag of technical-grade MOS2 powder online for a few dollars. There is no proprietary formula to protect, no exclusive manufacturing process, no brand moat. Compare that to a branded fuel additive. Companies like Chevron with Techron, or STP, or Lucas Oil invest millions in marketing because they sell proprietary blends, specific combinations of polyethyramine detergents, polyisobutylene cleaners, and carrier solvents that can be patented, trademarked, and sold at premium prices. A bottle of premium fuel system cleaner costs $10 to $25 and needs to be reapplied every few thousand miles. That is a repeatable revenue model. That is a business a corporation can build around. MOS2, by contrast, costs pennies per treatment and, because the solid film physically bonds to the metal surface, it does not wash away with every oil change. It does not need to be reapplied at every fill-up. From a business perspective, this is a terrible product to sell. Not because it does not work, but because it works too well for too long at too low a price. This is the pattern we keep seeing on this channel. Products and techniques that are genuinely effective, but commercially invisible because no single company has a financial incentive to promote them. Nobody held a secret meeting to suppress MOS2. It simply fell into the gap between works great and generates shareholder value. And in an economy driven by marketing dollars, what does not get marketed might as well not exist. That said, MOS2 is hardly obscure in every market. WWII Moly, the German company literally named after this compound, sells MOS2 engine oil additives across 150 countries and is one of the most respected lubricant brands in Europe. Japanese and German fleet operators have used MOS2 additives for decades. The knowledge is out there. It just does not have a Super Bowl commercial. Part 6. The Treatment Protocol. How to do it yourself. All right, here is the practical part, the reason most of you clicked on this video. Let me walk you through how to use MOS2 as an engine oil additive in your own vehicle. This is based on established practice from commercial fleet operations and the published research we have discussed. Step 1. Choose your materials. You need technical-grade molybdenum disulfide powder with a particle size under 2 microns. This is critical. Coarse powder can settle out and potentially clog oil passages. Look for technical-grade or lubricant-grade MOS2 from reputable suppliers. A 100-gram bag typically costs $5 to $10, and contains enough material for multiple treatments. You can also purchase pre-formulated MOS2 oil additives from established brands like Liqui Moly. Their MOS2 engine treatment has been on the market for decades and takes the guesswork out of particle size and concentration. Step 2. Determine the ratio. If you are using raw powder, the research suggests a concentration of approximately 0.01 to 0.5 weight% relative to your engine oil volume. For a typical 5-quart oil system, that means roughly 1 to 5 grams of MOS2 powder. Start conservative, around 1 to 2 grams for a standard 4-cylinder engine. If using a commercial MOS2 additive, follow the manufacturer's dosing instructions on the bottle. Step 3. Application. Warm up your engine first, drive for 15 minutes. The oil needs to be at operating temperature for proper circulation and to help the MOS2 particles reach all contact surfaces. Then, with the engine off, add the MOS2 powder directly into the oil filler opening. If using powder, you can pre-mix it with a small amount of fresh engine oil in a clean glass container. Stir thoroughly for 60 to 90 seconds and pour the suspension into the engine. MOS2 will not dissolve. It forms a grey suspension, which is exactly what you want. Step 4. Drive normally for 500 to 1,000 miles. During this period, the circulating oil carries the MOS2 particles to every friction surface in the engine. Under the pressure and heat of normal operation, the particles physically bond to the metal. You may notice a smoother idle and reduced engine noise within the first few hundred miles. This is the MOS2 film forming on bearing surfaces. Step 5. Reapplication. Because MOS2 forms a solid film bonded to the metal, it persists through multiple oil changes. Most fleet operators reapply once per 30,000 to 50,000 miles as a maintenance touch-up, not at every oil change. Part 7. What MOS2 cannot do. The honest limitations. Now, I would not be doing my job if I gave you only the good news. Anytime someone tells you a product has 0 downsides, that is the moment to start asking harder questions. So let me give you the honest limitations. First, MOS2 reduces friction and wear. That is what it does. It does not fix existing mechanical problems. If your engine has worn piston rings, leaking valve seals, a failing head gasket, or a damaged crankshaft bearing, no additive, MOS2 or otherwise, will fix those issues. You need a mechanic, not a mineral. Second, particle size matters enormously. If you use coarse MOS2 powder, anything over 2 microns, you risk particles settling in oil passages or being caught by your oil filter before they reach the surfaces where they are needed. Always use technical or lubricant-grade powder or stick with a pre-formulated commercial product where the particle size has been engineered properly. Third, there is a legitimate debate among engine builders about MOS2 and copper-based bearings. Some molybdenum compounds can be aggressive toward copper, and while most commercial MOS2 formulations include copper deactivators, these deactivators can degrade at elevated temperatures. If your engine uses copper alloy bearings and you want to be cautious, consult your mechanic or choose a formulation specifically tested for compatibility with your engine type. Fourth, MOS2 performs best in non-oxidizing environments. In the presence of oxygen and temperatures above about 350 degrees Celsius, it can oxidize to molybdenum trioxide, which does not have the same lubricating properties. In a properly lubricated engine, this is generally not a concern. The oil environment limits oxygen exposure at contact surfaces. But it means MOS2 is not a magical coating that works identically in every conceivable condition. Fifth, the fuel savings claims you see floating around the internet range wildly, from 3% to absurd numbers like 90%. Be skeptical of extreme claims. Peer-reviewed research shows genuine friction reduction of 19 to 26% at the tribological level, which translates to real-world fuel economy improvements that are meaningful but modest, typically in the 3 to 8% range, depending on your engine's condition, driving patterns, and baseline efficiency. Over a year of driving, that still adds up to real money. But anyone promising you a 90% reduction in fuel consumption for $2 is not being straight with you. Part 8. The Maintenance Mindset. Lessons from Automotive History. MOS2 is not a magic bullet. It is one tool in a broader philosophy of preventive maintenance, and that philosophy is the real survival skill here. So let me close with a few habits that cost nothing and can add years to your engine's life. The cold start. When you start your car in the morning, the oil has drained down to the sump overnight. For the first few seconds, critical components, especially turbocharger bearings, are running with minimal lubrication. Give your engine 30 to 60 seconds at idle before driving aggressively. In winter, give it a full minute or two. This costs you nothing but patience, and it dramatically reduces wear during the most punishing moment of your engine's daily cycle. The cool down. If you have been driving hard, sustained highway speeds, hill climbing, towing, your turbocharger's exhaust side housing can exceed 1000 degrees Fahrenheit. If you shut the engine off immediately, the residual oil trapped in the turbo bearing housing can carbonize into a hard deposit called oil coking. Just idle for 1 to 2 minutes before shutting down. Let fresh oil circulate and carry the heat away. Some modern cars have electric coolant pumps that handle this automatically, but many do not. The monthly thermal flush. Modern engines, especially in urban driving, rarely operate at sustained high temperatures long enough to burn off light carbon deposits. Once a month, get your car on the highway and hold it at a moderate elevated RPM, around 3000 to 3500, for 20 minutes. This sustained thermal cycle helps clear carbon from the combustion chamber and exercises the variable geometry vanes in modern turbos. Old mechanics called this an Italian tune-up, and the principle is sound. The quarter tank rule. Your fuel pump lives inside your fuel tank, submerged in gasoline that acts as both a coolant and a lubricant for the pump motor. Running your tank down to fumes regularly overheats the pump and draws up concentrated sediment from the bottom of the tank. Make a habit of refueling at a quarter tank. It is a small discipline that prevents an expensive failure. These habits, combined with an MOS2 treatment every 30,000 to 50,000 miles, form a simple but powerful maintenance loop. No special tools, no expensive dealer visits, just knowledge applied with consistency. And that is the theme of everything we cover on this channel. The most powerful survival skill is not a gadget or a product. It is the discipline to use knowledge that already exists. Conclusion. Let me put this in perspective. A typical American driver uses about 500 gallons of fuel a year. Even a conservative 5% improvement in fuel economy saves you 25 gallons annually, roughly $90 at current prices. Over 10 years, that is $900 in fuel savings alone, not counting the reduced engine wear that delays expensive repairs and extends the life of your vehicle. Your investment? A few dollars in MOS2 applied a handful of times over a decade. That is not a 160,000% return. It is not science fiction, it is the quiet, compounding value of applied chemistry. The same chemistry that Swedish miners used on cart axles, that WWII pilots trusted to keep their rotary engines alive, that helped land humans on the moon, and that fleet operators have relied on for decades. The knowledge was always there. It just never had a marketing department. If this deep dive changed the way you think about your engine, subscribe to Oracle Prime. Leave a comment below with your vehicle, make, model, and mileage, and let us know if you try the MOS2 treatment. We will be tracking results because real-world data from real drivers is worth more than any advertising campaign. Share this with someone who deserves to know. And as always, keep your mind sharp, keep your engines clean, and never stop digging for the truth. We will see you next time on Oracle Prime.